Please be careful that not for n equals to 0, because for n equals to 0 it gives the maximum value. You see the other part, and for we have also seen e to the power minus 80 ut Fourier transform in both the domain, and also for e to the power 80 u minus t in both the domains. Then by summing these two signal, what will be the Fourier transform of the summed signal has been shown. And see very carefully how signum's function Fourier transform of it has been calculated or estimated using the Fourier transform of exponential signals. Here is an interesting or important thing that you should keep in mind, that as the signum function, what is the signum function for t greater than 0? It is 1. That means if you take the integration of the signum function, then what will be the result? From t 0 plus to infinite, that means it is really if you go integration, it is going on towards infinity. Therefore signum function is approximated using 2 exponential and subtracted one from the another, and this approximation based on when a tends to 0, you see e to the power minus theta or plus theta, if theta tends to 0 will give 1, therefore it will give me the signum function, and we got the result. In the same way, unit step has been broken in signum and signum function, and we have also calculated the Fourier transform of ut. Okay, so among this calculation, 2 things I want to once again repeat. One is that when a signal, we have calculated the Fourier transform of delta function e to the power minus j twice pi ct cos omega ct sin omega ct, and we have seen either whether we are using f or omega as the frequency domain representation, when a signal gt is multiplied by a cos or sinusoidal signal, the signal frequency is shifted to positive side and negative side. Look carefully, g of f is centered, or g of omega centered around 0, where the Fourier transform of gt and sin twice pi fct carries 2 frequency part. A is centered around 2 frequencies, one is fc, another is minus fc. This property that a signal when multiplied by a cosinusoidal or sinusoidal signal, we will obviously prefer cosinusoidal signal, because if you see carefully, if you multiply sine, there will be some sign change, and on the phase also changes, one on the positive half and another on the negative side of amplitude. Therefore we will follow, basically use cosinusoidal signal, we will multiply that signal by the cos signal. Why? If a low frequency signal, that means you are working with this signal, and the signal frequency is say 3 kilohertz. You cannot transmit this signal for a long distance, as its power will be very low. So what you do, you multiply this signal. This is time domain representation, this is frequency domain representation. This is the bandwidth of the signal. No, this is not the total bandwidth. For as it is a low pass signal, the bandwidth is here. Okay, it's the total duration. So here we see that if you multiply this signal in the time domain, in the frequency domain, if we analyze the frequency domain, the signal whether we multiply in the time domain, then what will happen? You see, you will get two signals. Two signal, one centered as at Fc, it is Gf minus Fc, and one centered at minus Fc, it gives G A plus Fc. Okay, this property is very important, and you see, as you will more you will set this value of Fc, that means you will have to multiply this signal by a cosinusoidal signal, and the frequency of this cosinusoidal signal, if it is Fc, more will be the frequency of this carrier signal, more the signal will be shifted to higher frequency. This property is widely used or is the heart of communication engineering for long distance traveling. In the notes, you can also see how to calculate the energy of a signal. You see another name given. One is Rayleigh's energy theorem. Try to see the derivation, and one problem has been also solved for this calculation. To calculate the energy of a signal, you can just see this. It may come in the examination. Thank you. That's all for this week.